Hi, and welcome to Lecture 2 for Intro to Computer Science. Today we're going to talk about data manipulation, so things that we can do with the data, how a computer actually does things, and we're going to learn a little bit more in our Python code to add to our Python toolbox. So let's get started. First, we need to talk about the computer architecture. So starting at the beginning, let's take a look at how a computer deals with data. So each computer, no matter what size or what kind, has got some type of central processing unit or a CPU. Or sometimes we just call it a processor. In modern computers, it's going to be a small chip mounted directly onto the motherboard. So you can see here, let me get my pen going. In modern computers, it's going to be a small chip mounted to the motherboard, so something like these two here. There are two on this motherboard, so it is a dual processor. And also in very small computers, such as your smartphones or tablets, they're going to be much, much smaller. So because of that, we actually call them microprocessors. So what is in the CPU or this central processing unit? Well, there are three main parts that are found within the central processing unit. You've got an ALU, a CU, and you've got registers. So an ALU is an arithmetic logic unit that's going to perform any type of operations on your data. Next, you have a control unit, or that CU, and it's going to control the activities of the computer. And then finally, you have these registers. There's going to be two different types. You're going to have a general purpose and a special purpose. We'll talk about special purpose in a little bit, but let's talk about general purpose first. So the general purpose register is going to temporarily hold the data that you're manipulating. Okay, and it's also going to temporarily hold the result of the ALU if there's anything passed back, but basically it is just a temporary storage location within your CPU. Now, once that register has the result, it needs to do something with it. So it's going to get on a bus. No, actually it does get on a bus. But a bus in computer terms is nothing more than wires or some sort of connection between two locations within the computer. So the bus is then going to take that information and deposit it into the main memory of the computer for it to be used later. In the beginning, computers were pre-programmed with existing one and only one task. So you could have one computer dedicated to mathematics and one dedicated to databases, and that was all they knew how to do. Luckily, computers have come quite far since then. So computers nowadays are much more flexible thanks to this concept of stored program. A program is going to be instructions for the computer that are in fact stored in the main memory. So the biggest problem in early computers is that the CPU had the instructions and the memory was had the data, and none of that was mixed. So what they came up with was a concept of actually putting the two together and allowing both to reside within that main memory. That's where this stored program concept comes in. If you want to execute this stored program, you need to speak the same language as the computer. So let's go back to a little bit of binary. What your computer speaks is called machine language. And when I say speaks, I'm just meaning what it understands. We already discussed that last lecture. All it understands is off and on, 0 and 1. So it's going to be looking like binary. Well, in the grand scheme of things, we call it machine language. It's an encoding system based on the binary numbering system, which is going to collectively allow your computer to understand what you're asking it to do. So when you look at a single operation, we actually call that a machine instruction. So here we've got some high-level languages, and what we're working in with Python is a higher level language which allows humans to speak machine language, in essence. Machine language looks much more like what's here at the bottom when you're looking at the binary code. So there are two main philosophies that CPUs will follow when understanding machine language. So the first philosophy is that the CPU should execute the minimal number of commands as possible. Okay, this is called the reduced instruction set, or RISC. The CPU is going to have very limited number of instructions, but it's going to lead to efficient, fast, and much cheaper CPUs. Now, on the other hand, the other philosophy is going to be the other end of the spectrum, okay? These are going to be CPUs that are going to be able to handle a much larger number of operations, much more complex operations. This would be the complex instruction set computing approach, that CISC down here at the bottom. Here, the thought is that the CPUs can more easily handle increasing complexities that we have in today's society and in today's culture. No matter which philosophy your CPU belongs to, the CPU is going to have instructions, and these instructions can be grouped into 3 different categories. All CPUs need instructions on how to transfer data, how to perform basic arithmetic logic expressions, and how to control the computer. So let's take a deeper dive into each one of these 3 instruction types. So first, we're talking about data transfer instructions. These are just the instructions that are moving data from one location to another. It's going to load data, it's going to store it, it's going to copy it. A lot of these types of instructions are input-output instructions. Am I going to display something? Am I waiting for something from the keyboard? And it's going to communicate with devices outside of that main memory, so keyboards, screens, any type of peripherals. We're just talking about moving data around. We're not actually doing anything with it. In order to do something with your data, we want to look at our arithmetic or logic instructions. This is going to tell the control unit activities that it wants it to do. This is going to be your basic math and your basic logic, like those Boolean operators and those gates that we talked about. Finally, your instructions can be of a control instruction. This is going to direct the execution of the program, not the data, the program. So you have something called jumps. There are unconditional jumps and conditional jumps. Now, a jump is just going to be a take me to another location, take me to another address. An unconditional jump is just go to that specific address. A conditional jump, on the other hand, is if something happens or if something is true, then go to that address. So they're just slightly different. Now, in order to understand the machine language a little bit more efficiently, we're going to use something that is going to be a theoretical machine, and it's going to help us illustrate that machine language, okay? Our book uses something called a VOL model, and it's very simple and it's very, very easy to use, okay? It's just a simple representation of a hypothetical machine, okay, that speaks a hypothetical machine language. We're going to be using it to see kind of how the insides of those instructions and those, how the computer does what it needs to do. So our VOL is going to have 16 registers that you can see from here. It's going to go from register 0 to register F. And notice we're using hexadecimal notation, sorry. So we've got register 0 to F. Each register is going to be 1 byte, so 8 bits. So we've got from 0x0 to 0xF. I don't know why my mouse is being weird, but that's okay. Our VOL is also going to have some main memory over here on this right-hand side. And remember, each hexadecimal number is 4 bits. So here we've got, we're going to go, each register is 1 byte. So each register has 8 bits. So we're going to go from 0, 0, 0, 0, 0, 0, all the way down here to 1, 1, 1, 1. 5, 6, 7, and 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So that's going to give us 256 cells in there. So this is what our bit patterns are going to look like. Okay, now that we have our VOL set up, let's look at the different parts of machine language. So each instruction that the computer receives in machine language has two different parts. The first part is called an opcode or an operation code. It is going to be the elementary operation. Do I want to print? Do I want to add? Do I want to store? The rest of the instruction then is going to be indicated as the operand. That's going to have detailed operation info. Now, the interpretation of what is in the operand is going to be based on which opcode you have. We're going to see some examples of this, so don't get stressed out. Okay, we're going back into our VOL model. So let's have a 4 hexadecimal digit being used as an instruction. So our instruction here is going to be a 35A7. That is a terrible 7. There we go. I don't know why it jumps on that screen. A7. Okay. So the first hex is going to be the opcode. That's what this is showing you right here. The very first value is the opcode. So our 3 is our opcode. The rest of them put together is going to be our operand. So let's take our instruction of 35A7 and let's take a quick jump into Appendix C of our book and let's see what it actually means. Okay, so I put a little snippet of Appendix C here in the notes. So luckily 3 is towards the top, so that's good. I could get a little bit more of what is in the table. So we've got that 35A7. So the opcode is 0x3. If we look into this table, we're going to be right here. Okay, so this is our row. Okay, you can see by looking at that row that the basic command is a store. Okay, what you also find out is what the operand is. See, it says right here, operand. So our operand, the R is going to be 5, and the X is going to be A, and the Y is going to be 7. Okay, that's how you're going to read it. Reading the description now, we can see that our instruction of 35A7 actually says to store the bit pattern found in register 5 in the memory cell whose address is A7. Okay, very easy to decode, very easy to pick it out and see what it says. Okay, so your R is your 5, your A is your X, and your 7 is your Y. The book has lots of different examples of this that you can work through. All you have to do is find what the opcode is, which is always going to be that first numeral or letter. Go into Appendix A, find the opcode in the first column, and then it's going to tell you all the other information that you need. That opcode is going to explain to you the operand, and there's going to be a short description. Now that we have a better understanding of a single machine language instruction, let's take a look at how a program is going to actually execute. Computers are going to follow a program by moving those instructions in and out of the CPU as it needs to. To understand how the computer knows what to move and when, we need to look at 2 special registers. Remember I said a minute ago that we're going to look at special registers. These are going to be the registers that control the program execution. We have an instruction register and a program counter. Now the instruction register is going to hold the current instruction. So like what we just saw, it's going to hold that hexadecimal number. The counter is going to hold the address of the location of where the next instruction is so that it can go get it once it's done with the instruction that it has. Now, one cycle is when we fetch, decode, and then execute. So we're going to do these 3 simple steps repeated over and over again until the program is done. So let's take this program execution back into our VOL computer model and let's see what it looks like. Okay, here's a great example of our VOL computer with instructions already loaded into some main memory. This example is going to retrieve some memory or retrieve some values and put them together. We're not really worried with what it's going to do. What we're worried about is how the program executes and the steps that it goes through. So first, it says that the program counter is at 0A0. So your program counter is basically has this information in the main memory, okay? So it's in the main memory address of A0. Since A0 is the first address of the program, that's the address that's put into the counter. Okay, let's look at the first step now is fetch. Now, we're going to perform the fetch step of this cycle. The fetch step is going to take the address in the counter, load the instruction through the bus into the register of the CPU. Now, one thing that we know is that our instructions are 4 hex numbers, remember? And you can see here in the memory, there's only 2. So what we need to do is we need to do 2 in order to get the complete instruction. Okay, so our program counter goes over here and says, I need the instruction 15, 6C, and that's what's given back through the bus into the register. Okay, that's how we find out what our instruction is. Now, before we decode this instruction, there is one thing that we have to do. So the program counter has got to be set with the address of the next instruction, remember. Okay, so you take that address, that's the start of the next instruction, and you put that in the program counter. Now your fetch is officially complete. Let's quick go into Appendix C and decode what your instructions of 156C actually means to do. Okay, luckily again we're at the top of the numbering chart, right? So I can use the same table I used before. So in this example, our opcode is the first digit, which is a 1. So I can go into 1 and it tells me my RXY. So my opcode is 1, my R is 5, my X is 6, and Y is C. So according to the table in Appendix C, 0x1 says to load the register. Okay, so we're going to load register 5 with the bit pattern found in memory cell whose address is 6C. Okay, because you want to load register R with the bit pattern found in the memory cell whose address is XY. So the computer would then execute this instruction as its last step. These 3 steps then are going to be just repeated over and over and over again until the end of the program. Some of the instructions are to move and store, some are going to be arithmetic, logic, and shift operations. So let's take a quick closer look at the different types of operations of the instructions. First, let's look into the arithmetic logic instructions. Now, these we're going to go more in depth with our operators here in just a second, with our and, our or, and the gates that we used in Class 1. We're going to look a little bit more in depth into some shift, and we're going to discuss math just really quick. It's going to be really easy, I promise. So we looked at these logic operations. We looked at single bits. Okay, so we only had an input of a single bit. So we can expand that to include as many bits as we need, and this is called a bitwise operation. So for bitwise operations, you just take each bit starting at the right, working your way left, and you do whatever the operand is. So, for example, we've got a 1001 and a 1100. What do you think the answer to that would be? Well, a 1 and a 0 is a 0 and a 0 is a 0 and a 1 is a 0, and a 1 and a 1 is a 1. So your result is a 1000. Okay, easy. Just take each bit directly. Now let's look at an OR example. We're going to have the same 2 inputs. We're going to have 1001 and 1100 for an OR. Okay, let's see what changes. So 1 OR 0 is a 1, 0 OR 0 is a 0, 0 or 1 is a 1, and 1 or 1, not exclusive, is going to be a 1. Okay? So your answer of 1001 or 1100 is going to be 1101. You just take them each bit by bit. Now, let's take a quick look into that rotation and shift operations. Now, there are different types of shifts, and shifts are just moving things around, okay? There is a circular shift, which we call a rotation, a logical shift, and arithmetic shifts. So here is a good example of the circular shift. So your original bit pattern is right here. You're going to take the very last bit and you're going to circle it around and put it in the front, and then everything else shifts to the right. That's all there is to it. So your final bit pattern is going to be the last digit and then all the digits that came before it. Now, a logical shift, what all a logical shift is going to do is replace this last bit with a 0 and then move on with life. That's it. And an arithmetic is going to basically leave the sign bits unchanged. Okay, so that's the only difference. Let's look at some of these basic math functions. Now, when we're just talking about math in a sort of a theoretical global, idea. So we can look at addition and subtraction as being similar operations, right? If you subtract something, you're actually adding a negative, correct? So you can perform those identically. They become the same operation. Multiplication, in fact, is actually just addition over and over and over and over again. And then in the same token, division is really just subtraction repeated many times over. So if you look at mathematics, at least the 4 basic operations in that way, then all you really need your CPU to perform, if you're looking at that the least amount of commands, is an addition command. You can actually perform addition, subtraction, multiplication, and division if you just have an addition instruction. Okay, subtraction is just addition with signs. Multiplication is just addition over and over again, and division is an addition with signs. That's really all there is to it if you look at it from the most abstract point of view. Now, machine language is not easy for humans to understand, right? We don't look at all these ones and zeros. I get cross-eyed. This is why we have what we call those higher level languages, like we saw in that for one of the first slides, such as Python. Python is going to change all of the commands that you give it into machine language that we were just looking at. That's what Python does. So a single Python command, it could actually be 1, 10, hundreds, thousands of machine instructions all built into one Python command. The programmer does not need to know or have any understanding about the CPU, which machine language philosophy it uses, is it reduced or complex, how does it went. The programmer doesn't need to know any of that information. So just imagine though, we've done variable assignments, and one variable assignment would at least contain a load, a store, and move opcodes. Okay, so think about how many opcodes some of the arithmetic expressions and even a print would have. Speaking of Python, we're going to add a little bit to our toolbox today, and if we want to control what our program is going to do in certain conditions, we can use something called a control structure. So we're going to talk about 2 different ways today. The first way to control a program is with an if statement. For example, if your water temperature is too high, if it's above 140 degrees, the water's too hot to take a bath. That's called a single control. It's only going to execute one time and then it's going to move on the program. On the other hand, you have a multi-control, and we're going to use what's called a while statement. This is going to execute until a certain condition is met. So you're going to do it repeated over and over again until you meet a specific condition. You could read this example by saying, while n is less than 10, print out the n and then add 1 to n. Okay, so if I say, for example, n equals 7, there we go, and I go into this loop, okay, it's going to print 7, it's going to print 8, it's going to print 9, it's going to print a lot more pretty than how I'm doing it here. and it's going to print 10. Now when it prints 10, it's going to add 1 to it, be 11, and then this is no longer going to be true, and it's going to ignore and move on to the next step. Okay, it's just a way for you to do things in a conditional manner and to control where your program is going. Now, Python also uses something called a function for its programmers. We've actually used some functions already, like print. Print was a function. It's a keyword, but it's because it's a function. A function is going to define operations that should be done with any kind of parameters that you give to it. It's like a mathematical function. Okay, if I have the function x equals y, let's say y plus 2. There's my function. If I say x equals y plus 2, and then I say that y is going to have the value of 1, then the function set tells me that x is going to be equal to 1 plus 2, or x is going to be equal to 3. A function in programming does the same thing. So when we use a function, we say that we create a function call, so that when we're typing the print statement, those were actually function calls. We were calling that function. Functions are just a shortcut in programming to make your code much less complex and much less hard. How about how much easier? Much easier to understand by the programmer. Let's take a quick look at this example here, and your function here is max. Let's put a box around it. There we go. Given these three numbers of x, y, and z that I have typed here, you can see what max is going to do is it's going to choose the largest of those three numbers. Well, we know by looking at the numbers that your max is going to be the 2000 number. But in reality, this function is going to mathematically compare all three of these values to find the largest one. Okay? And so when we say print, it's going to print the 2078. Now, we don't need to know the nitty-gritties of how the max is actually comparing these numbers. Is it comparing the hundreds and thousands first? Is it comparing the ones first? It doesn't really matter to us. All we need to know is what it's going to actually do and what it's going to send back. Now, functions have some different things that are associated with it. So one thing I want to point out is that you can give something to a function by using what is called an argument. In the previous example, we sent it x, y, and z. So those were arguments. This argument is then most likely going to be used by the function to either do something, compare something. It's going to need it for some reason. So for example, when we used the print function before, we sent it in the parentheses the quotation string that we wanted it to print. That quotation string within the parentheses, that's the argument. We can change what the print does by just sending it different arguments. We sent it arguments that had numerics with strings. We can change to what the string says, but every single time it actually output and printed to the screen. So functions can do two things. It can either send something back, or it doesn't have to send something back. So returning a value means that the function wants to give something back to the original program. The print function that we used does not return any information, okay? So what we used as a print is called a void function or a procedure. It's just going to do something. It doesn't need to actually tell us anything back. Now, this example on the screen, however, it is going to return something. What it's going to return is, it is going to return the square root. Okay? So this math.sqrt is a math function of sqrt, which is going to calculate the square root of whatever number that is, and it's going to send me back the square root. Now, when I get the square root back, I'm putting it into the variable hypotenuse. Okay? Now, if your function does have something that is returned, it's sometimes called a fruitful function because it has a return value. So let's take a second and let's play with a little bit of code. Okay, the first thing we're going to do, we are going to type out the code that we just used that we were just looking at for the hypotenuse, but we're going to add one more thing into our toolbox. We're going to allow the user to enter in their own information. Okay, so now I've got my screen up and going. I'm using Python Anywhere again, just because it's easy right now. So I opened up a new file and I called it lecture2.py just for your information. Let's go ahead and type in the first line, and as we remember, the pound sign or the hashtag means that it's a comment. So this is going to calculate the hypotenuse, ENUSE, of a right triangle. Okay. Now, another new statement that we have is something that says import math. Another thing that we have that's new is import math. That is going to allow us to use a bunch of the functions that are available to mathematics. Okay, we have another comment here. It's going to say inputting the side lengths first try. Okay, now we need a variable. Side A is going to be equal to, we want our number to be an integer. When a user does any input, it automatically gets that input as a string. So in order to make it so that it is an integer, we have to put the type int in front of it. So we want it to be an integer. Now, the command that we use in order to get user input is input. We're going to send it a string. Length of side A. And make sure you have enough parentheses. Now I'm going to hit save here. Okay, I'm going to go ahead and run this file and run the console. So you can see here, and I may need to move my little head. So length of side A, let's say it's 15. That's all it does. Okay. I just do that to see if it's working. Maybe look at some of the formatting. So I don't like how this question mark and what the user is inputting is so close together. So I'm going to go ahead and put a space up here. Okay, so let's do side B. And we're going to do it the same way. We're going to use that input length of side B, question mark, space. Okay. Last but not least, we are going to put another comment in here. We're going to say calculate third side based via through the Pythagorean theorem. The THEOREM. Oh yay. Okay, so your hypotenuse is going to be equal to math.sqrt square root of side A. Remember, double asterisk is power, 2 plus side B, double asterisk, power. And let's print out that hypotenuse. Go ahead and click save. Let me come over here. Let me move myself over to the center. There we go. Now you might be able to see better. Let's hit run. Length of side A, 3, 4, and because we know with Pythagorean theorem that a triangle is a 3, 4, 5. So it goes ahead and prints out 5. Okay, let's take another look. Let's make a longer program this time. So what we're going to do is we're going to create a program and it's going to have some functions in it. And we're going to call it Marathon Training Assistant. We're going to go through and create the function, and then I'll go to the next slide that has some more instructions on how to use the function. But let's go ahead and let's save the one that we did. Let's go to files. Let's create a new file. And lecture2b py. Okay. So let's start off by doing the comments. Marathon Training Assistant. TANT. Don't worry about your spelling because mine's horrific. Okay, we're going to import that math because we're going to use some math functions. So it's good practice to put a few comments at the beginning, the first comment being the name of it, of what your program is or what it's going to do. And then before you actually start getting into things, it's good to have a small explanation as to what it's going to do. So this function converts a number of minutes and seconds to seconds. Okay, you can do it on multiple lines like there is in the example. You can do it on one line. It doesn't matter. It's up to you. Okay, so we're going to create two separate functions in this. And the biggest thing with Python is that you do have to create the function before you use the function. So in order to create the function, use the word def, D-E-F. It is a keyword and it means to define something. Now, what comes after the def is the name of your function. So let's say total seconds. And then you're going to put parentheses, and inside the parentheses you want those arguments. So what do you want to send to this? Well, what we want to send is minutes and seconds, right? Because remember, it's going to convert a number of minutes and seconds to all seconds. You hit the return key, and now we start doing the instructions for that function. In Python, it is, what you need to do is you need to hit the tab key or indent the instructions for that function. Now what we're going to do is we're going to do a return, and we're going to send it minutes times 60 because there's 60 seconds in a minute, and we're going to add on to it the number of seconds. Okay. One thing I forgot is at the end of your definition statement you have to put a double dot or a colon mark to indicate that this is the end of the title and we're actually going into instructions. So I apologize. So you're going to have definition, the name, the arguments, and the colon. Okay, let's create our second function. So this function calculates Okay, so this function is going to calculate a miles per hour given a time in seconds. So let's define it, DEF for define. Let's give it a name. They called it speed. And what it's going to expect is a time, okay, in seconds. Again, you need that colon and you have your indent. Now what we want it to do is to do that conversion, so let's say return, there are 36 divided by time. Okay, let's go ahead and save. We can actually run this. It's not going to do a whole lot of anything because there's no input, there's no print statements, but it will compile. Okay, so you can think of it that way. Let's go back over here. Let's get the second portion of our program up and going. So now we're going to get into, we have done all of the functions, now let's get into the nitty-gritty of our program. So let's do another comment to explain what we're doing. So we're going to prompt the user for pace and mileage. Okay, so we want the pace in minutes and in seconds, and we want miles. All three of these are going to be just like we did the input, so we want numbers first of all, so let's make sure we use the int to make them numbers, and then we're going to use input. Okay, whatever's in the quotes for the input, that's going to be your prompt for the user, so minutes per mile. Okay, an integer, input, seconds per mile. Okay, and then make it an integer, and the last thing we want is input total miles. Remember, white space doesn't matter, so my line 16 and my line 15, it doesn't matter. It's going to treat them pretty much the same other than the string that I sent it. The next thing we're going to do, I'm going to put another comment so that we know what we're doing. We're going to calculate and print the speed. Okay, so my miles per hour is going to be equal to speed, and we're going to send it some information, right? Okay, so we had speed, we want to send it time, but time has to be in seconds. So in order to get it all in seconds, we're going to do total seconds. Okay, so let's do total seconds, and we want to send it pace, minute, pace, seconds. Okay. Now that we've done this calculation, let's see what it looks like. So print your speed is plus str miles per hour, because we want to make sure it's a string, because remember we calculated a number, so it's going to think it's a number. Okay, plus space mph. Okay. Now the next section, we're going to put another comment. It's going to calculate the elapsed time for a planned workout. Okay, so your total is going to be equal to miles times total seconds. Okay, with your pace minutes and pace seconds. Okay, so your total is going to be however long you did it for seconds times your miles. Okay, so elapsed minutes is going to be equal to total, divided by 60. Now remember, what does this divide do that the other one doesn't? It takes the whole number only, and it doesn't pay any attention to the decimal place, right? And so your elapsed seconds is going to be total, the remainder of what's left over. Now remember, it's not the remainder in terms of tens, it's going to be whatever the remainder is. So that's how many seconds we have left over. Finally, let's print it all out. So your elapsed, time is, let's change all of these numerics that we have on line 24 and 25 into strings so that we can print them. Let's say minute. There we go. Your elapsed time is blank minutes, blank seconds. Okay, that's what it's going to look like. Let's go ahead and hit save one more time. And let's click run. Okay. Minutes per mile. Let's say we do 10 minutes per mile. How many seconds? Let's say 23. For, let's say, 3 miles. Okay, so your speed is going to be 5.78 miles per hour, and your elapsed time is going to take 31 minutes and 9 seconds. Okay, you can see how we took the division here, and we calculated some speeds and things like that. So I hope that this gave you a little bit more understanding of going into Python and doing some more commands. I'm going to do another quick video for assignment 2 so that you guys can get a little bit of additional information on those. Otherwise, if you have any questions, comments, or concerns, please let me know, and I will see you next time.